Right. In the previous video, we talked about the effective actions and effective potential. We derived the effective actions, including the quantum effect. So especially let's review on the previous one. The first one we talk about the generating functional and the Biederer transformation. We obtain the effective action, and before that there are also the generating function of the connected diagram. So if we derive differentiate such a generating functional quantities, then we can obtain the endpoint correlation function with the several type. First of all, in the chart, we can obtain the all the diagram, but for the W, we can obtain the connected diagram, but the case of the gamma effective action, we can obtain the one-pi diagram. And today, so we'll talk about the Colemann-Weinberg potential. From this effective action, this includes all the quantum effect, especially the one-pi diagram. So first of all, we use a background field method. So we can decompose some quantum field with the background field pi b and the quantum fluctuations pi. And we will integrate out such a quantum fluctuation so that only the background fields remain. If we decompose this pi field in this path integral formalism, then there will be the d pi, which is the quantum fluctuation and integrated out, only the pi b's that remain. So if we consider the following scalar field with the chaotic term potential, then we can decompose the pi with the pi plus pi b. Then there will be some terms that only consist by the quantum fluctuations, and sometimes that considered by only the background field, and there will be some of the cross term here with some symmetry factors. Such as symmetry factors can be obtained by the combinatorics of the field. If we collect the term which is only consisted by the background field, and becomes Lagrangians with only the background field, but the other terms becomes the lambda prime of the pi and the pi b. So the point is there's such a combination of the pi and the pi b should be integrated out by the d pi. So these terms are integrated out, and we drop all the tadpoles, just the first order terms of the pi's here. So the Lagrangians of the background field terms are just get out because this is the independence of the quantum fluctuation pi. So here is the some purely quantum fluctuation terms and several cross terms and the other term, and because we dropped all the tadpoles term, this term should be disappear. So only the even terms are remain. So that we can obtain not even terms. So these terms remain. So that we drop the tadpoles of the burst order of the quantum fluctuation field, so that we can classify the kinetic terms, and other terms comes from the derivatives of the potentials about the background field. So here and because we want to consider the second order term, so only the second derivative terms remain here, and by the Gaussian integrations for the quadratic term in the exponentials, then we can obtain the such a determinant term, and yeah, this is general one, but we want to consider the scale step now. So after that, let decompose so this is the generating functional, and the effective action can be obtained by the exponential of this. Yeah, here is the effective action now. So if we decompose the effective action with the three-level terms and the quantum loop effect, then quantum loop effect is taken by the logs of the one of the roots of the determinants for the quadratic term. And by the exchanges of the log and the determinant, then it becomes a twice random log here. And some constant terms go inside in the logarithm, so that the inside of the log become the dimensionless quantity. And such a second derivative of the potentials about the background fields becomes the effective mass of the background field. This depends on the pi v. We assume that here, so originally the pi x is the function of the space-time, so that this was a functional, but now the way we consider pi b as the constant of the space-time, so the pi b is just a function. I mean, this m effective becomes just a function, and such a special the time integration becomes just a volume times time. Yes, so the just remaining term becomes like that. So if we transform it in the momentum space. And now, just continuing, this was equations we obtained. And by the Wick rotation, we can convert from the Minkowski space to the Euclidean space and impose the cutoff for the such Euclidean momentum with the lambda. And under the spiral coordinate, so we can obtain the results of the integrations. And they assume that that cutoff is extremely larger than the effective masses, and we can approximate this sort of the log like that. And then the total effective actions is considered by the such a term for sort of the three-level term, and the constants because we assume that the background is the constant of the phase time, so the kinetic term becomes 0, and the loops term. And if we divide the effective fraction by the minus spatial volumes at any time, then we can obtain the effective potential now. The effective potentials are consisted by the three-level part and some constant and the constant times of the effective mass cast, but this is uninteresting, such as shown on the C2's pipe independence. This is dependent on the regular realizations of the renormalization. So the only important part is such m effective both powers and the log with m effective scales of the sum regularities, which is right from the quantum loop level. So here is our math. First of all, we use the background build method by the decomposing sort of the build with the background build and the content fluctuations, and we integrate out the content fluctuation, then we can obtain the effective action. During the path integral, we use the Gaussian integrations for the quadratic term over the exponential, and by the dividing by the minus volume times time, then we can obtain the effective potential, and that it contains the logarithm of the some effective mass term. And we call this such a quantum level term is the Colemann-Weinberg potential. So remind that the renormalization, we assume that there are renormalized quantities of mass and the coupling and some cosmological constants for the scalar potential. And we can define the effective mass as a second derivative of the potentials, and this includes the interactions like the electric system. Then we can define the effective potential, first of all, effective potentials with the three-level C1, C2 times effective mass and the logarithm term, and then we will insert such a v second prime, v second prime, v second prime as the effective masses. So we will insert such a term now. And by imposing the renormalization condition, at when the pi equal to the pi r renormalized field, and we can define the several quantity like as the cosmological constant at the renormalized scale and the cortical coupling and the mass lambda or mr. Now we can obtain the some coefficients like that as effective potentials, and generally we call this as the Colemann-Weinberg potential. So the effective potential considered by the three-level term and there's some additional sign about depending on the particle spin is the Fermions rules of boson, and there are degrees of freedom of the particle, and there will be the effective mass, volt power. This is the scarce effective, and the logarithm of the effective mass scarce over the renormalized Biot scale. So for example, if we add the Yukawa coupling here, then such interactions will contribute to refractive mass in such a secondary potential. Then this gives the additional Colemann-Weinberg potential, and this determines the standard model Higgs potential stability, whether the lambda is the quadratic term coupling is positive or not. And the dominant contributions of the Yukawa coupling comes from the Tapcock mass because it has the largest Yukawa coupling.